I'm going to give a talk about human AI co-design of computational morphing matter. I will frame it in a different way as like my previous work, but I will just talk through all my work, but in a way like talking about like optimization. So I think everybody heard about optimization or machine learning, and like design a lot. But actually, inherently, everything is about like optimization. Everything is following this framework, and I will talk about what does it mean by like optimization as everything. So usually, when we're doing design, we always start from solution space. The space can be like your sketch or like AI or like 3D modeling software. And the solution is like you will find a specific subset of that design space. For example, you will like have a subset of the sketch from the whole like AI sketch space. And that's your solution, which is your specific sketch or 3D model. And then the model, so this 3D model is different from this model. So this model is an abstract process that will take in your input and output something called a performance. And this performance can be like aesthetics or the geometry or the color. So, and in this process, the optimizer, it can be human or it can also be like AI or anything else that can process the information. And this loop means based on the performance of your model, the optimizer will change a little bit of the solution and make it better. And so it sounds very familiar and it's very similar to something like iterative design. For example, you have 3D model, you want to iterate on this design, you will have the initial guess of how this shape look like in the solution space, which is like 3D model space. And then you will go through a model, which is like the human cognition. You will like look at the model and feel it and think about how you like it. And you will output something called maybe aesthetics. Is it looks good or not? And based on the aesthetics, you optimizer, which is also the human, will continue doing the CAD modeling to improve the solution and make it better. I think everybody have been going through this process every day for your homework or hobby. And a lot of things can follow in this pipeline, like sketch, painting, design a web page, or write a poem. What you're doing is you're doing graphics design, web design, and text editing. So in this process, there is no AI. There's only like computer helping you to do the design part, but there's no AI here. And how about like morphing matter plus AI instead of like sketch plus like human designer? So what we can do here, so there are actually two processes. One is called forward design. The other is called inverse design. And in this process, in the forward design, the optimizer is still human. The solution space can be a lot different from the previous page. So then I will talk about my projects as examples. For example, there's a project called Thermorph. In this solution space, the solution is a kind of thermoplastic 3D printing toolpath. That's our solution space. And what it's about is, so basically the end output of this project is you print a flat sheet, it will turn into a 3D sheet. When you heat it up, it will automatically transform without any interference. And how we came up with this idea is actually if you have any experience in 3D printing, you will see the 3D printed objects were like layer by layer stacked together. However, sometimes you will see something like this, which is one corner will pop up. It's called a war page because like the plastic will uncontrolled, or sometimes it will go out of control and it will contract more than you expected. When you heat it up and it will deform. So it's quite similar when you pour like hot water into a plastic bottle, it will just shrink. So usually there's a defect in 3D printing, but what we did was to try to leverage this defect. Okay, so basically the 3D printing material there is a very chaotic like polymer chain inside the material. And this is a very chaotic but stable status. When you print it on the printing platform, it's quite like squeezing the toothpaste onto a platform. You are squeezing and also stretching the polymer chain inside the material. And then it will quickly cool down and lock in this straitened status, which is not the preferred state. It has a lot of energy, try to contract. So when you peel this off and put this into the hot water, it will, so if it's on the platform, it cannot contract. But if you put into hot water or you peel it off from the platform, it will contract. And at this moment, if you have another layer, which is this gray layer at the bottom that's passive, that cannot contract, if one layer contract, the other does not contract, it will do something like bending. So that's a very simple basic mechanism behind this thermoplastic. So practically what we did is printing a layer of called PRA that can contract, and another layer called TPU that's flexible, so it does not include any energy and it will not contract. So these two actuator give some energy by giving heat, it will do the bending. And there's simulation showing, yeah, it will really do the bending. This is so-called model inside the optimization pipeline. And so why there is a forward design? Because yeah, the previous example is quite simple. It's just a single bending actuator. But if you want to turn something into rows, it's quite complicated. You need to understand what will happen at every corner. Is basically here you will bend like perpendicular to the radius direction. But if it's the whole pattern, you need some tool to help that. So that's the forward design part. So you have a tool that will simulate how the bending will look like if you give certain folding pattern. And you start with a flat outline of the rows, and you give some assigned like bending crease pattern, and then turn into this model. This model will tell you the output is how it will do the transformation into rows. So in this case, the output of the model is shape, but it's also a shape along the time dimension. It's a transformation process. Okay, this is the first example, a forward design for morphing matter. The second example is the more flower project, which the solution space is just flower, which we can buy from like Whole Food or Giant Eagle. But it's a specific solution, sub-solution space that is to giving some specific groove on top of the flower to make it into something that can turn into a helical or like curved geometry. And so this is the first project Lin did in MIT. It was not flower, but I just give you an idea about how it works. So you have like different edible material, and each of them have different swelling ratio. Basically, you put them into hot water, they have different like volume change. And you can see like some part with another with gelatin like swell less than the other parts. And this is the first project. Is basically you instead of adding groove, you are attaching some extra material on the top, and it will turn into a bilayer structure and to turn from the initial flat shape to the final curved shape. And this is like a saddle shape and helical shape. And then the second part of this project is like published last year, is like by adding groove. So in this case, the material is more pure and I would say elegant, because it's only pure flower. Any flower you can use can work here. So what you're adding now is not adding another different swelling ratio material, but you're adding some groove. So you're actually utilizing the geometry in this flower. So if you imagine the whole piece of flour put into the water, it will just swell isotropically into a just larger pasta. It will not bend at all. However, if you have this kind of groove, then you will see the center of the groove is very hard to let the water to penetrate through. So it takes more time for this part to fully swell, but the thinner part can easily swell. This causes a difference in the swelling ratio on the two sides, and this flour will bend up. So similar to the thermoplastic in the previous example, this groove is the simple principle in this project. However, you can go crazy by combining a lot of small groove in different geometry, different arrangement, and then a very simple bending mechanism can turn into a lot of different geometries. And to visualize all these things without really making it, what you need is a forward design tool with a simulator. And as you see here, the simulation can quickly show you how it will look like after you're given this groove instead of physically making it. And it can do like all a different shape of pasta. Like there are like more than 200 types of pasta. and there are 60, like theoretically, there are more than 60 types of pasta are feasible with this technique. But the origin of this project is very simple. It's just a single bending actuator. Okay, so the third project in forward design is called Electric Pop. I'll just quickly go through this. So as you can see here, you are actually drawing something in Adobe Illustrator on the right-hand side, and you will see a transformation on the right-hand side. And then in the real world, you can see what you saw in the simulator really happen. And the mechanism is something maybe a lot of people have played with when you're a kid before. So it's called a Mylar sheet. It's kind of sheet can accumulate static electricity. And when you give electricity, it will repel from each other and eventually turn into a quite like large shape compared to the initial volume. And there is Arduino board to do the control part. Oh. So this Arduino board will do the control part, and then you will do the design in AI and Adobe Illustrator. And this is kind of like called what you made is what you see design. So all your drawing here will be the laser cutting pattern. And at the real time, this laser cutting pattern will be rendered or like remeshed to a triangle mesh on the right-hand side. And then a simulator will at the real time to show you how it will look like. So you can quickly do the iteration and see how your design will look like in the physical world. And so there are rows and some popping up installation, or you can like flag package. You can like send a very small piece of thing to your friend and it will pop them into a tree or a Christmas tree. Okay, so here are the three projects about forward design, but actually the new mesh project I introduced last week is also a kind of forward design tool because we have a simulator tool. You can quickly iterate through and without really physically making it. So here the simulator is, so one key part in this work, of course, human is important here. Another thing is simulator is important. You need simulator to be fast and accurate. And the core part to the simulator is you need to really understand what's behind all this material. And you need to simplify this physical model to make sure the simulator can run fast and accurate. And so far, all the performance is about the shape. And then I will talk about the inverse design part. So you can imagine like right now the pasta is still quite simple. They're all like folding structure, but if the pasta go crazy into something like your face or like an egg or like a dog, it's very hard even with a forward simulator to think about how to design this flat pattern to make into 3D. Instead, you might just want the AI to tell you, okay, I just want a dog. How can I make this flat pattern? So here comes with the inverse design tool. In this case, the optimizer is not human anymore, but the optimizer is AI. And also, okay, so this is the new mesh. This is the geodesy project, which is also thermoplastic, but this time it's not a developable surface, it's a non-developable, which is a double curvature geometry. And so basically, instead of manually assigning where to do the folding, you directly input the target shape, which is like facial mask or face. And the algorithm will automatically tell you how you should do the 3D printing. So here is the 3D printing toolpath. And the color means what's your printing speed or your printing layer thickness. And you just need to send this to your like 3D printer and print it, and then put this piece into the hot water. It will turn into your initial input shape. So human save really a lot of effort of designer in this process. What time is it now? Okay, I will go quick. Yeah, so the mechanism here, basic mechanism is almost the same as the thermal project, the folding rose flower project I just mentioned. You print thermoplastic onto platform, you take it off and put it into hot water, it will contract. It's very simple. And so in the thermal, you have 2 layers, so it will bend up. And in this project, you only have a single layer. So if you only single layer, what will happen is the material will only contract in your printing direction, and it will not contract much, or it will actually expand in the other direction. So that's the basic mechanism in this project. And then you can imagine if you only print one direction, it will only contract in one direction. But if you print in a circular direction, what will happen? It will quite similar to you opening up an umbrella. So the radius will not change, but the circumstance will contract. And eventually it will turn into a dome shape. And the color here shows the contraction ratio of the material. So the redder, the more it will contract. If all the colors are the same, it will turn into like an umbrella, like a cone shape. And so you can easily understand what's happening before, but if you want to make some shape that's more organic and arbitrary, like a mountain, like with two hills, how can you arrange this flat pattern here? So that's the part we need an inverse design tool. And specifically in this project, what we did is there's a specific meshing process to turn into a triangle mesh along the z-axis. And then there is a flattening algorithm to flatten the mesh from left to right, and at the same time capture the contraction and elongation ratio of all the parts. And then there is specific toolpath planning method, because in 3D printing, you have to do everything in one stroke. You cannot have discontinuous line, but you still need to fill the whole surface and along the direction we assigned. So there is toolpath planning, and eventually what you can get is what you input is just a 3D model with color texture, and what you output is a 3D printing pattern and the color pattern. And that's the end result. So another project about inverse design is one step further to the flower. So the pasta, previously we were always doing like initially design the 2D pattern and see how it morph. But actually what we can do is you just input a rose flower 3D model, and it will tell you how your printing groove pattern should look like. And this groove principle is actually pretty general, so it can go to a lot of material like gel, like gelatin, like hydrogel, and plastic, shrinky dink. So a lot of shape changing material can use the same mechanism and use the same inverse design tool and show the same geometry. So I would say it's like all these tools are getting more and more general, both in the algorithm wise and also the material wise. So it seems like inverse design is saving a lot of energy of human and give us a much better life. However, what can we go even further is, so far all the performance is only about the shape, but actually people care more about the shape. For example, you might care about the motion and the gravity, and which is like new mesh project I just mentioned last week. So you can assign a lot of target in addition to the shape to new mesh. For example, you wanted to locomote to towards forward. It's just like a robot. You wanted to turn left or turn right. For example, this is a lobster. You wanted to move forward. What we did here is we only tell it your goal is to move forward. And after a lot of iteration, the AI will tell you how to assign these channels and how to give the contraction ratio. It can do this forward locomotion. And the other one is, instead of like move in a straight line, we wanted to rotate. So we want this dog or cat to like fall down on the ground and stand up by itself. So it's like orientation change. But we didn't do like manually assigning any beam to this cat. What we did is I wanted your like vertical orientation to flip 90 degrees and then come back. And after a lot of iteration, the tool can automatically figure out this configuration. And the left bottom side is a table that we tell it to like move forward, and it can move forward. It can also like do the rotation and tilting the platform angle. So these are about locomotion. And I also mentioned before that what we are working on right now is you can try to change the gravity and gravity allocation of your mesh mesh geometry. So in addition to giving a target shape, you can also giving a target gravity allocation, or the center of gravity. By allocating where to give the liquid, the new mesh can make sure the object looks right and also feels right in your hand. And so here is the inverse design with more performance. And what's next is like, maybe you can go even crazier, like how about emotion, semantics? What can you get from these shape-changing objects? So shape-changing, the first thing you think about is like the feeling, you touch it, you can see it, it might give you some emotion. And here are some like example from other work. Like this is Ruta, a previous robotics PhD's work. What she did is she did a lot of crowdsourcing to understand like how like spider robot locomotion can give people what kind of feeling. And the right top is what kind of geometry can give people what kind of feeling, like which is more like busyness, one is more casual. And left bottom is people explored how to 3D print different shape with different like spiky level or like number of units can give people what kind of feeling. Is it, do you feel anger or do you feel like happy? And the right bottom is like what kind of geometry give you what kind of atmosphere in a room. If it's different chair, will you feel different? So I can see there are a lot of potential to combine the shape and transformation and all these semantic and emotion feelings. And that's what we are interested, I am interested in doing in the next semester. Yeah, feel free to give ideas or questions about all these. Yeah, thanks.